So let's see what applications does the limit arithmetic theorem has. So let us maybe consider this first application of this theorem. So that's a simple corollary. So we've proved actually that whenever we have product of two sequences, then that are convergent, then their product is also a convergent sequence, and it converges to the limit, which is the product of the limits. And so, but we didn't prove the property that if the sequence an converges to L, then this limit, if we multiply the sequence by some constant alpha, some scalar, then the limit will be alpha times this limit. It is quite intuitively, it can be proved directly from the definition, but let's see this way of thinking, which is proving this using part 2. So now suppose, consider the constant sequence Bn, which is just the constant sequence alpha. And so clearly this sequence converges to the limit alpha because the distance between Bn and alpha is 0 in the absolute value, and so it's smaller than any epsilon, any positive epsilon for every n. So of course, according to the definition, the limit of Bn is alpha. And therefore, if we consider this limit of alpha times an, it is the limit of an times Bn. And now by what we have proved, since an converges to L and Bn converges to alpha, then the limit of the product exists and it equals to the product of the limits. And okay, it's somewhat backward thinking, but I wanted to introduce this way of thinking that we have already proved this part that we needed to prove anyway, so we can now use it. Okay, so let us see another application of the limit arithmetic theorem. So we have seen sequences of this form, and so it is intuitively clear that the limit is supposed to be 3/5, and it can be proven directly. Something similar has been done, even for more complicated sequence. But now let us see how to apply the limit arithmetic theorem. And here we will make rigorous this intuitive argument to say that, okay, when n is really large, billions of billions, then this 4 is really insignificant, and this 5n is really insignificant compared to n squared. And similarly with this 1 and this 7n, and therefore this roughly behaves, the numerator behaves roughly as 3n, and the denominator behaves roughly as 5n squared, 3n squared on the top, and then n squared reduces, and it's 3/5. So now let us make it rigorous. So we use the limit arithmetic theorem. So first of all, when we divide the numerator and the denominator by n squared, then of course it is the same sequence. Numerically, this is just the same sequence, so nothing has changed. And now we have actually several applications of the limit arithmetic theorem. So this 3 is a constant sequence, and therefore its limit exists and equals 3. Now, if we consider this sequence 5 over n, then 1 over n, it was proved that it converges to 0. And so by just a statement that we have said, 5 over n would converge to 0 as well, because this is a constant, and therefore the limit of 5 over n would be 5 times the limit of 1 over n, which is 0. Similarly here, the limit of 4 over n squared, by the same argument, is also going to be 0. Therefore, the limit of the sequence on top is actually the sum of 3 limits, right? It's of this convergent sequence, and this convergent sequence, and this convergent sequence. This converges to 0, this converges to 0, and then by the limit arithmetic theorem, the limit of the sequence on top exists and equal to 3. And by similar argument, the limit of the sequence, it's now 3 sequences, 3 applications of the limit arithmetic theorem, exists and equals to 5. And since 5 is non-zero, and this sequence is non-zero for every n, then by what we have proved, then the limit of the quotient of those two sequences on top and of the bottom exists, and it equals to the quotient of the limits, and therefore this is justified. So for the first time, you need to really elaborate on all those parts, like I did here, just to make it rigorous. But then this kind of reasoning, it becomes clear, and we don't really need to say every time this very elaborate justification. It becomes clear, but when you do it the first time, you really need to explain exactly how the limit arithmetic theorem here is being applied, and why all the steps are justified. Okay, so now let us prove another theorem. Suppose that we have two convergent sequences, and an converges to some limit a, and bn converges to b, and suppose starting from someplace. So let n0 be some fixed natural number. And suppose that starting from this index n0, an is no bigger than bn for all n that is greater than n0. And n0 could be hundreds and hundreds of billions, doesn't matter. It's important that it starts from someplace on. And this inequality holds actually for infinitely many elements of the sequence. As we were reasoning, when we were talking about limits, what's important is what happens for infinitely many elements, and what happens to finitely many elements of the sequence can be ignored. So if this inequality holds, starting from someplace, then the limit of bn is bigger or equal to the limit of an, which seems intuitively clear. And so let's see how do we prove it. So suppose that a was actually, it was the case that a is bigger than b, right? And we'll assume that, and we'll derive a contradiction. And from this contradiction, it will immediately follow that a has to be less or equal than b. And so the idea is that, okay, this sequence n is going to be as close to a as we please, and bn is going to be as close to b as we please. And now suppose that a is bigger than b. This means that a minus b is positive, and let's take half of this distance, right? We will see another proof for metric spaces, and we'll see the general reasoning. So we can choose this epsilon, and by our assumption, here's the point. This epsilon is going to be positive. So now we actually use the definition of the limit. So we have a natural number n1 and a natural number n2, such that the distance of an minus a is smaller than this positive number epsilon, which is strictly bigger than 0, according to this assumption. And we have a number n2 such that the distance of bn from b is smaller than this epsilon. And now, you probably guessed the next step, we choose the number n epsilon to be the maximal of those two numbers. And then those two conditions are going to hold simultaneously, and we'll see how we derive the contradiction. Okay, so we choose n of epsilon to be the maximal of all those, actually 3 numbers, so that, we need this inequality to hold, and we need those 2 inequalities to hold, so we choose n of epsilon to be the maximal of those 3. Okay, and okay, for every n that is greater than n of epsilon holds that an is bigger than a minus epsilon, but if you remember, epsilon was a minus b divided by 2, and if you bring this to common denominator, this is what we get. On the other hand, n is greater than an epsilon, and an epsilon is also greater than n0, and therefore this part of the inequality also holds. An is no bigger than bn starting from n0, and n is bigger than n of epsilon, that is greater than n0, so this inequality holds as well. Now we know, since n is greater than n of epsilon, which is greater than n2, then bn is smaller than b plus epsilon. And now again we use the definition of epsilon as being a minus b divided by 2. And if we bring this to common denominator, we get a plus b over 2 again. So here's the contradiction. We have that the number a plus b over 2 has to be smaller than a plus b over 2, and this is a contradiction because no number is smaller than itself. 5 is not strictly smaller than 5. And yeah, this is the contradiction, which means that this contradiction implies that a is no bigger than b. Yeah. Okay, so now we have an interesting corollary that all sequences that are convergent has to converge to a unique limit, of course. And let's see how are we going to use this previous proposition. So suppose that we have a sequence that converges to 2 limits simultaneously. Now this, of course, cannot happen because the sequence has to be as close as we please to the limit, and we can actually prove this directly, but we will rely on this proposition that was just proven. What we can have is that for sequence, we can have 2 distinct partial limits, but then the sequence does not converge at all. We will prove that if a sequence is convergent, then it has only 1 partial limit. That is, every subsequence of this sequence has to converge to the same limit. But anyway, suppose that this is the case, and converges to some number L1 and L2 simultaneously. Okay, now we actually take two sequences. So we have a sequence an, and we can take another sequence bn, and bn would be an. And now, since n is smaller or equal to an, and n converges to L1, and n converges to L2, by what we have proved, L1 has to be no bigger than L2, and similarly L2, by exact same argument, by traversing it, has to be no bigger than L1, which implies that they must be equal. Okay, so now let us prove this theorem for metric spaces. So suppose we have the notion of a distance, and we have a sequence that converges. And a sequence. So this sequence, if it converges, I should have said that if a sequence if the sequence n converges, then it converges to a unique limit. I will fix the slide here. I should have said if. Okay, so suppose that the limit of an is L1 and the limit of an is also L2, but now in a general metric space, because previously we relied on the distance of the absolute values. So the idea now that if those two elements, L1 and L2, are distinct, suppose that we have two distinct elements, then it is equivalent to saying that the distance between them is strictly greater than 0, because in a metric space, the distance between two elements is 0 if and only if it is the same element. So it is equivalent to saying, assuming that those are distinct is the same as assuming that those that this is positive, strictly positive. Yeah, so it's equivalent to saying that L1 and L2 are distinct. And so we're going to prove it, this same argument, but now we'll take, so previously we took epsilon to be half of the distance, but for this to be even more clear, we'll take epsilon to be quarter of the distance. So we choose epsilon to be quarter of the distance between those elements. And so let's see what happens and how we derive the contradiction. So on the one hand, an has to be as close to L1 as we please, and it will be smaller than this epsilon. And on the other hand, an has to be as close as we please to L2, and it has to be smaller than this epsilon starting from some place. And so what happens here is that an cannot be simultaneously as close as we please to L1 and as close as we please to L2, because it cannot be closer to both of them than quarter of the distance. We'll see how it unfolds. So there exists natural numbers ni such that the distance of an from li is smaller than epsilon for l greater than ni, of course, for I equals t1 and 2. So this is like an abbreviation. For, of course, L1 there exists a number n1, and for L2 there exists a number n2, such that those conditions are satisfied. So this is like a bit abbreviated writing. So let's see what happens. And so now if we choose n of epsilon to be the maximal of those two numbers, then for every natural number n that's greater than n of epsilon, we must have the distance. And I wrote this on purpose. Of L1, the metric is symmetric here. So the distance from L1 of an is smaller than epsilon. And at the same time, the distance of an from L2 also has to be smaller than epsilon. So where's the contradiction? It will come from the triangle inequality. So using triangle inequality, let us consider this distance between L1 and L2. So now this is no bigger. So now you see the reason for writing it this way, so that the triangle inequality becomes more apparent here. So the distance, this is no more, the distance between L1 and L2 is no more than the distance of L1 to an, plus the distance of an to L2. And now this has to be smaller than epsilon, which is quarter of the distance, right? And this has to be smaller from the same epsilon. Than the same epsilon. So here we have this is smaller than epsilon plus epsilon, which is 2 epsilon. But epsilon is quarter than the distance, quarter of the distance, which means that the distance between 1 and L2 has to be no bigger than half of this distance. Well, how can this be? This means that if we transfer this positive number to the other side, it implies that this has to be, actually, we can say strictly, this has to be strictly smaller here. Sorry, for the equality here, I meant strictly smaller here than epsilon plus epsilon, which is 2 epsilon. So here, sorry for the error in the slide. Here it's supposed to be strictly smaller, and we get that if we multiply by 2, that this distance is strictly smaller than 0, which is the contradiction. It contradicts the assumption that metric is non-negative. Of course, even if it was equality here, if it was smaller than equal, then the distance between L1 and L2 being smaller or equal to 0 implies that this distance has to be equal to 0, which means that L1 and L2 is the same element in the metric space, contradicting the assumption that the distance was positive here. So that's a contradiction. This means that sequences in metric spaces have to converge to a unique limit. In fact, in topology, the most general condition that that guarantees uniqueness of limits, I think, is the well, at least in Hausdorff spaces, we will talk about this later. We also have unique distances, but this is quite a general setting. So every metric space is a Hausdorff space, but this is just as a side remark. Okay, so let's move on. So this contradiction, of course, implies that the distance between L1 and L2 has to be 0. And if we look at an illustration of what happens in this metric space, so this is L1 and this is L2. And of course, there is this line connecting them, and we have this distance between, it's not necessarily a space where there are lines, but this is just visualizing. So there is this distance between L1 and L2, and we can demand if the sequence converges, if this distance is positive, of course, right? Then we take a circle here, or actually a ball, with radius which is quarter of the distance, and then all the elements of the sequence has to be, their distance from L1 has to be smaller than this epsilon, which is quarter of the distance. So all the elements has to be here, and this is another quarter of the distance, so all the elements has to be here, and this is smaller than the quarter of the distance, and this is a contradiction because those two inequalities cannot be satisfied simultaneously. So because this is this epsilon is smaller than quarter of the distance, and this doesn't add up, when you can see this clue to this triangle inequality, which doesn't add up. So in metric spaces, limits are unique. Okay, and so here we have another proposition, which is useful. Suppose that we have a sequence n which is bounded, and suppose that the limit of the sequence Bn is 0. Then the limit of the product sequence exists, and it is 0. So let us give a proof of this fact. So suppose that n is bounded, of course, it is given. So let m be this positive number such that every element of the sequence is smaller than m for all natural numbers n. This is just stating that the sequence n is bounded. Now the sequence Bn converges to 0. So there exists, since Bn converges to 0, there exists a natural number n of epsilon such that for all n that are greater than n of epsilon, holds that the distance of Bn minus 0 can be small as we please. This is just Bn, and we can choose this to be smaller than epsilon over m. But what does this say about the sequence of the product? Well, let's see. We chose this to be epsilon over m on purpose because this means that for every positive epsilon there exists a natural number n, such that for every n that is greater than n of epsilon, and this is this n of epsilon for which Bn is bounded by is smaller than epsilon over m, then for this n of epsilon, which is guaranteed to exist, we have that for every n that is greater than n of epsilon, if we consider the sequence which is the product, so the distance of an times Bn from 0 is just equal to an times b in absolute value, and this is smaller or equal, since an is bounded by m in absolute value, than m times bn. And now bn happens to be bounded for every n that is greater than n of epsilon by epsilon over m, and when we take this product, we see that the distance of an times bn from 0 is smaller than this epsilon. And so we have proven that for every epsilon there exists n of epsilon such that for every n that is greater than n of epsilon holds that the distance of an times bn from 0 is smaller than epsilon, which means that the limit of the sequence is 0. Okay, and so now let us see an application of this. So let us look at this sequence, which seems complicated. We have seen sine of n to the power of n. Of course, the sequence n to the power of n grows like crazy fast. And the sine of this is just, a crazy function. This sequence really wildly oscillates, and we divide this by n. But what we have to remember here, we can significantly simplify matters here, because the sine function, whatever is inside is in the absolute value, placed over the reals, is bounded by 1, right? So it is bounded, so this is a bounded sequence. And 1 over n converges to 0. So, so we see that sine of n to the power n is no bigger than 1. And the limit of 1 over n is 0. And therefore, by the previous proposition, we have that the limit of sine of n to the power of n over n tends to 0.